This video introduces an application of matrix algebra or linear algebra, which is computer graphics and animation in two-dimensional space. So let's say you wanted to draw a triangle, two-dimensional triangle. Then in the computer, you can store a triangle in the computer using vertices by assigning vertices and put all the vertices into a 2x(n) matrix. Okay, so look at this look at this triangle. So the first vertex is 0 and 0. The second vertex is 1 and 1. And then the third vertex is 1 and -1. Once we have the three vertices, we can just connect these three vertices together to create a triangle, right? How can we translate all of the vertices into a 2x(n) matrix? We come up with this matrix. This is a 2x(n) matrix, 2 rows and n columns. So 2 rows means each of the column vectors in this matrix represents the xy coordinate for a vertex. So 1, 1 is here, 1, -1 is here, right? And then because we want to connect this point to this point, this point to this point, and this point back to this point, that means we always want to include the point of the first vertex at the end of the matrix. So these 3 columns represent for the 3 points, and then this is just the same coordinates of the first point because we want to make a loop. All right, so we know how to come up with a 2x(n) matrix that is a representation for a set of vertices that is making up a triangle. Well, so this is how we set up a triangle. And then we can use linear algebra to do animations with this triangle. Okay. Linear algebra, more specifically, we're going to use linear operator. First, dilations and contraction. Okay. So in order to do to create dilations or a contraction for a graph or for a picture, or more specifically for this triangle, as we're using as an example, we use a linear operator of the form Lx equals to c times x. So x here is a matrix, right? Representing all the vertices of this triangle. And c here is a constant. So if c is greater than 1, that means you're making a dilation. And c is less than 1 and it's greater than 0. I mean, you're making a contraction. So the operator Ln is represented by the matrix C times I, where I is a 2x2 elementary matrix. For example, if we in two-dimensional space, if C equals to 2, that means you want to dilate this triangle by 2. Then the matrix A, the matrix representation for this dilation is 2, 0, 0, 2. You take 2, multiply by the elementary matrix. Okay. And in order to find the new coordinate of the triangle, after you dilate it by 2 units, you take A, which is the representing matrix for this dilations, and you multiply to X, which is the matrix representing for the original triangle. You get the new matrix. So reading this new matrix, you know that this is the first vertex of the new triangle. This is the second vertex. This is the third vertex. And also, this is just the first one. Okay. As you can see that you dilate this original triangle by 2 times. Just expand it 2 times. And again, if you want to contract it by a certain unit, you want to set C is in between 0 and 1. So you make it a smaller triangle. The next one is reflections about an axis. I mean, you have a triangle, right? You want to reflect this over the x-axis, or you want to reflect this over the y-axis. Again, you want to use linear operator. The linear operator is the mean that we can find the matrix as you apply a map, this map onto the unit vector E1, you get E1. And then if you apply this map onto the second unit vector, you get negative E1. If you want to reflect a vector or a graph about the x-axis, right? You want to do something like this. So if you start here, then after you reflect it, you have it here. And then as you can see, when you reflect it, you keep the same x coordinate, but the y coordinates is flipping from positive to negative, or otherwise, or reversely from negative to positive. So that's why E1 is staying, but E2 is negative than negative E2. So it follows that the matrix A, the matrix representation for a reflection about the x-axis is 1, 0, and 0, negative 1. And again, if you take the matrix A and you multiply to x, you get a new set of coordinates. And you can see that 0 reflected over the x-axis stays the same, you know. Becomes this point here reflected over here. And then 1 will go back here. Okay. And if you look at, this is the original triangle, and this is the one after you flip it over the x-axis. See that the blue and the red sides are switching the side. Okay. And similarly, if you want to reflect a vector, you know, about the y-axis, which means, so I have a vectors here, and I want to reflect it over the y-axis. So the new one will be this one. So the y value stays the same, but the x value is flipped from positive to negative, or from negative to positive. So that's why you have this as your linear transformations, and you can translate it using matrix representations. And the matrix representation for reflection over the y-axis is negative 1, 0, 0, 1. And again, you apply this to x, which is the matrix of the original triangle, and then you got a new set of coordinates for the new triangle. So this is the original one, and this is the one that reflects over the y-axis. You can see 0 still stays 0. Negative 1, 1 should be here, right? Negative 1, negative 1 down here. All right. So this is about reflections over an axis, right? Either x-axis or y-axis. All right. Now, how about rotation? Rotation, you can use a linear transformations that rotates a vector about the origin by an angle of theta in counterclockwise directions. So the linear transformations and the matrix representation for this rotation linear operator is cosine theta, negative sine theta, and cosine theta. Well, let's say that if you want to rotate a triangle by an angle of 60 degrees counterclockwise, the matrix A's will be cosine of theta of 60, right? Negative sine of 60 and sine of 60, cosine of 60. And this should be your matrix representation for rotations over rotations counterclockwise of an angle of 60 degrees. So after taking this matrix multiplied to x, I got new coordinate. And the new coordinates here, so this is the original triangle, as we know, and 0 here, so say 0, right? And then this is this first from 1 to here, and then it's rotated 60 degrees counterclockwise. And then if you look at the third vertex, it's from here. If you rotate it 60 degrees counterclockwise, it's go from here to here. So using linear transformations for graphic animations, you can easily translate a picture in a different, using different effect, rotations, dilations, contractions, flipping over the y-axis and x-axis. Okay. And then translations, you're moving an object up and over. Unfortunately, translations we cannot use is not a linear transformations, because you're gonna take a vector x and then you wanna, let's say if you wanna move it up by 2, it's not a linear transformations. So then L cannot be represented by a 2 by 2 matrix. We need to use a different system. And the new system that we're going to use is called homogeneous coordinates in order to do translations. So what is homogeneous coordinates? So now this coordinate system is formed by equating each vector in R2 with a vector in R3, having the same first 2 coordinates and 1 as the third coordinate. For example, if this is a vector in R2 and you want to translate this vector into a vector in R3, reserving the same entries on the first 2 entries, but always assign a 1 as the third entry. So then if L is a translation by a vector A in R2, right, we're still working in the 2-dimensional space for our graphics. We can find a matrix representation for L with respect to the homogeneous coordinate system. And it has to be a 3 by 3 matrix. And we're first starting with the 3 by 3 identity matrix. And we replace the first 2 entries of a third column with the entries of A. Again, A here is the translation that you want to do. If you want to move up by 2 and move over by 3, then you have y equals to 2 and x equals to 3. Right? So that's how you come up with the translation matrix, entries A. For an example, we want to translate our triangle to the right by 2 units and up by 3 units. We use vector A as 2, 3. So A, 2 is according to x, right? And 3 is a corresponding entries of y. So you move it to the right 2 and up by 3. Then you can come up with the matrix representation for these translations. Again, A is, so you start with an identity matrix, I, 1 0 0 0 1 0 0 0 1, And then on the third column, you replace the third column by 2 and 3 and 1. And 2 and 3 and 1 here is the vector in R3 that we get from our translations, 2, 3, and we translate it to the homogeneous coordinate system. Okay, so this is A. We have A, and we have the original matrix for our triangle. But again, if you look at the first two rows, it's the same as the matrix that we found. We came up earlier, but the last row are filled with ones. And then we have new coordinates for our triangle. And the new coordinates will be, so if you take the first two rows of the new matrix to get the new coordinates, and the last row, it's more or less like a placeholder in R3, right? It will be R1s. We can ignore it for now. So 2, 3. So we move from 0 to 2, 3. Which makes sense. And we move from 1, 1 to 3, 4. Right? 2, 3. And we moved from 1, -1 to 3, 2. So all the vertex or all the vertices are moved up by 2 and over by 3. And using this homogeneous coordinate system, we can do translations in two-dimensional space for two-dimensional graphics. All right, so this video introduces how you can use linear transformations, more specifically linear operator, in R2 and R3 in order to do graphic animations. And the four basic effects or animations are dilations, contractions is one group, reflections over axis is another group. You do rotations counterclockwise, or if you want to do rotation clockwise, then you have to come up with a slightly different matrix compared to A, right? Rotations, and the last one is translations, but you have to translate your system into the homogeneous coordinate system in order to do translations effectively.